Yeah, so last time we started the evaluating the binary classification performance. So the easiest way is to make a contingency table to see what's happening. So we have basically the two categories. So it's binary classification. So we have predicted values and truth. So predicted values are either negative or positive, or null or alternative. So this is okay. So negative and positive, and the predicted class is also negative and positive. And if we make the count of observations, for example, this is 20, this is 5, this is 10, this is 40, you can see for example, the sensitivity and specificity. So in this case, the specificity is what? The 20 over the 25. So 80% specificity, and also maybe this is not really the best example, so maybe we change the number. So if this is 50, then we predicted the 50 out of 60, the positives. So this is the 50 over 60. So sensitivity is the 83%. So specificity is equal to 20 over 25, so 80%, and sensitivity is equal to 50 over 60, so this is 83%. So that is what we did. And okay, so now we consider where is the threshold between predicted negative and predicted positive. And the most natural choice is probability of 0.5. If the predicted probability is more than 0.5, we regard it as predicted positive, and less than 0.5 predicted as negative. But we can set different threshold. If we want to have a higher sensitivity at the cost of lower sensitivity, then we can classify a person as default if probability is larger than 20%. So that is basically the set threshold around here. So in such a case, we have more observations. So probably this 25, 10, 50 becomes maybe 10 and 15, and maybe 5 and 55, for example. So in such a case, the sensitivity becomes 55 over 60. So that is the 11 over 12. So this is about 0.9. something, and the specificity is equal to the 10 over 15, 10 over 25, sorry. So this is 40%. So in this case, specificity gets smaller, but the sensitivity gets larger. So depending on the threshold, we can change the sensitivity and the specificity. So if we want to have a higher sensitivity, we have to be compromised with a lower specificity. Yeah, so this is another example of, the concrete example from the last time. So in this case, the specificity is, okay, so suppose that this is negative, this is positive, negative, and positive. And specificity is 9,400 out of entire 9,667. And sensitivity is 195 over entire 333. But if we change the threshold, then we can have higher sensitivity and lower specificity, or lower sensitivity but higher specificity. Yeah, here you can imagine, for example, we classify, we want to identify who are the hypertension patients. and we set some threshold on the blood pressure. If threshold is too high, we miss some risky patients. But if threshold is too low, basically we classify the healthy people as patient. So we have the trade-off between the two errors: the higher sensitivity, lower sensitivity or lower specificity. So that means that if we take the pair of sensitivity and specificity, then we have the negative relationship between that. And often the people in the diagnostic medicine use plot this 1 minus specificity and the sensitivity on XY plane. So you can see that the false positive rate, that is the 1 minus the true negative rate. This is specificity. So 1 minus specificity. And this is sensitivity. So in such a case, we have the positive relationship between two variables. Sensitivity and specificity have negative relationship. So sensitivity and 1 minus specificity has positive relationship. What's the perfect situation? So the perfect situation is sensitivity is 1 and specificity is 1. So that means 0, 1. So this is the perfect ideal case. So this is the perfect. If we have a perfect rule, then we get this point. But actually, it's not perfect, so that we have this kind of curve. Possibly, we have maybe this kind of curve. It's even worse. Maybe I should say a blue one. So if the classification is better, maybe like this. And the perfect case, just we have this point and this point and this point. So the rule, so if we want to make specificity as high as possible, then specificity becomes 1, but instead we will have sensitivity of 0. So if the test is very loose, we cannot detect any positive case. So that is this point. Yes. Or if the test is very strict and we regard every patients as positive, then sensitivity is 1, but specificity is 0. So this point. So usually the curve is like this. Yeah. And the random rule. With random rule, the sensitivity and the specificity, the sensitivity and 1 minus specificities are the same. So this is the random rule. So you can see that suppose that this table is entirely random, then the proportion of this to this is equal to proportion of this to this. For example, maybe the numbers should maybe 9,000 and 1,000 and here 900 and 100. Then that is basically regardless of truth. Basically, that we decide the predicted as no default and predicted as default. So this is random rule. So in this case, the sensitivity is 0.1, 100 over 1,000, and the specificity is equal to the 9,000 over 10,000. So 0.9. So 1 minus specificity is equal to 0.1. So random rule that we have this, the diagonal line from 0, 0 to 1, 1. So that means our so-called ROC curve, receiver operating curve, that is the blue curve. So this has the area under the curve between 0.5 to 1. If the rule is at least better than the random rule. And usually this area, so this area. So this area under this, the ROC curve, this is called AUC, area under the curve. So this is between 0.5 to 1. Yeah, so this is called AUC. So yeah, it depends on the context, but if AUC is only 0.51 or 0.55, that isn't really a good test. And if AUC is 0.8 or 0.9, so that is reasonably good classification rule. AUC can go below 0.5. That is possible if we, for example, on purpose make the rule which is worse than random rule. Then the AUC gets 0.4 or 0.3. But usually this test result is based on some statistical model. For example, we use logistic regression. Then at least we optimize the sign of the predictors. So for example, higher blood pressure has higher risk of heart attack, or lower blood pressure has the higher risk of heart attack. Then at least if that's estimated from the data, usually that model performs the better than the random rule. So AUC is likely to be larger than 0.5. Maybe if the test is very difficult and we use the training set and the test set, maybe we can get the ROC curve of AUC equal to 0.49 or something. But you can mostly assume the AUC is between 0.5 and 1. Yeah, so that is the concept of ROC curve and AUC. And this is better than accuracy, better than sensitivity and specificity. Because, for example, accuracy is based on just one threshold. So if threshold changes, then the result may change. But the AUC is more comprehensive measure. So if AUC is somewhat, for example, if you have two models and two AUCs are 0.7 and 0.75, it's likely that the model with 0.75 AUC is better. So this is more comprehensive measure. Yeah. So if you do binary classification problem, I recommend you to do AUC analysis. Because binary classification problem is really hard to get the robust results, because each response value have only the information of 0, 1. So I mean the 1 bit of information for one observation. So if we have 100 observations, that is just 100 bits of information. So that is different from continuous response model. Continuous response, the response has some number, continuous number. So that is like 3.54. So that has much more information than just 0, 1. So if you analyze binary classification data, then basically sample size should be very large to have robust results. And at least to get somewhat the robust results, using AIC helps compared to using just accuracy or sensitivity. Any questions?
So I'm not sure. Do you know if there's a way we can interpret AUC as some kind of probability, or do we just say it's the area under this curve, and that's the end of the day?
This isn't really probability. So yeah. Yeah, I haven't thought about it. Yeah, yeah, I think essentially it's not probability. Maybe it's not impossible to give some probabilistic interpretation, but yeah, I think usually not. Yeah.
Yeah.
Yeah, that's a good idea. Yeah. But yeah, usually not. Okay, so the next one is the QDA, quadratic discriminant analysis. So this is similar to linear discriminant analysis. but only the difference is that okay, so for each group that we fit the normal distribution, and in QDA, this variance covariance matrix is not necessarily the same across different groups. So basically, okay, so suppose that we have x-axis and y-axis. Suppose we only have two different predictors, x1 and x2, and we identify three groups, for example. Then maybe one group have correlation between x1 and x2. So contour plot is like this. And another group, maybe the contour plot is like this. And the other group, the contour plot is like this. So we allow that this kind of the different contour plots. So in LDA, so these three contour plots have the same shape. So the location may be different, but the shape of contours are the same. So this is QDA. And yeah, so okay, so suppose that our predictor, suppose that the X is, for example, R3. So three predictors. So in this, the graph shows two predictors, but suppose we have three predictors, then how many parameters are there? At first, the mu k is, okay, so suppose the maybe mu k is the mu k1, mu k2, mu k3. So the mean value of the three predictors for each group, the case group. Maybe for the previous example of the weight, the distinguish animals by weight, height, and neck length, the mu1, mu k1, mu k2, mu k3 is the mean weight, mean height, mean neck length of the case group. And sigma k is the variance covariance matrix. And the variance covariance matrix is the symmetric. So you can see the sigma k11 square, sigma k22 square, and sigma k33 square here. But the off-diagonal terms are symmetric. So that we have the sigma k12 square and the sigma k21 square, but these are the same. Sorry, these are the same. Sigma k21 square, but this one and this one are the same. So that means we only have the 6 parameters in this matrix, 1, 3 square and sigma 2, 3 square. So sigma k23. Okay. So basically, how many parameters? We have 6. 1, 2, 3, and 5, 6. 5 for 6. Well, for 5, 6. So we have 6 parameters. So each group we have 3 plus 6. So we have 9 parameters. And we have 3 groups. Suppose that the k is equal to 3. Then the number of parameters is for each group 3 plus 6. And we have 3 groups. So we have the 27 parameters. So there are many parameters, right? So this is the QDA. If LDA, we have much less parameters. So we can see the LDA, suppose that X is also 3-dimensional and K is equal to 3, then, okay, so number of parameters is equal to, okay, so 3 is the mu k1, mu k3, mu k2, mu k3, and we have 3 groups. So 9 parameters, and sigma has 6 parameters. So we have 15 parameters. So it's much, so there are much less parameters compared to this. So more parameters, more complicated, more unstable, but if real boundaries more complicated, QDA fits better than LDA. And the boundary between classes are linear in LDA, but hyperbolic for QDA. I think we will see some later, maybe, no? No, okay, so Yeah, so originally, the LDA is based on likelihood function of two groups and likelihood function of quadratic function of predictors. So originally that is quadratic the boundaries, but in LDA case the quadratic terms are cancelled. So that's why the boundary becomes LDA. But for QDA we don't have such reason. So in general the hyperbolic between the boundary between the classes. Yeah, so QDA is more flexible and QDA is more complex. So in case of k is equal to 3, sorry, I think it's a kind of complicated, so maybe I should, yeah. So suppose that P is the dimension of predictor. So P, so if three-dimensional, 3 times 4 divided by 2, so 6. This is the number of elements in sigma sub k. And we wonder, which is better, LDA or QDA in practice? And here are two examples. And the left one, okay, so at first I explained the situation. So the purple line is true boundary. So this is simulation study, and the purple dashed line is the true curve behind the simulation. So this is the true boundary between the orange class and the blue class. And the black dashed line is the estimated boundary by LDA, and the green solid line is estimated boundary in QDA. And which is better? And in the left example, LDA looks better. So you can see that the black dashed line is much closer to the purple dashed line. And simply because the true boundary is the linear. So, and the LDA assumes the boundary is linear. So that model is correct, basically. So that's why we can get the boundary correctly. Actually, we don't have many observations between these two boundaries, green and black. So in reality, the classification errors are similar, but at least this is simulation study and we know the truth. So we can see the boundaries are better for LDA. So potentially we have more observations here, maybe more blue observations here, more maybe also more orange observations. Our orange observations are fine, maybe here, but these blue observations are misclassified by this green boundary. Okay, so this is LDA better. But on the other hand, the right-hand side, the example, you can see the green line is much closer to purple line, and the black line is a little off. Actually, in this case also, we don't really have many observations between black and between black and the green. We have few observations. Yeah, we have few observations between this, but it's a little bit confusing. I think that we have some, noise in the simulation study. So this is actually below the true boundary of purple dotted line. So these should be the yellow points, but actually the one of the points are blue. So we have the simulation added some noise. So from this, actually, we cannot really see. From this data point, we cannot see. But since we know the true boundary of purple dashed line, the green line is, we know that the green line is closer to black line. Yeah, so basically, in short, which is better? So it depends on the data. And if the true boundary is linear, then LDA is usually better. True boundary is quadratic, usually QDA is better. Okay, so this is another more comprehensive simulation study to compare logistic regression, LDA, QDA, and KNN. And at first, there's some qualitative analysis. So both logistic regression and LDA have the linear decision boundary. So basically, these two models give the similar results. Slightly different conditions. So LR, logistic regression, is based on the LR is based on logistic regression, and LDA is based on the maximum likelihood of Gaussian densities. So slightly different conditions. And in terms of complexity, the KNN with small k is most complex rule. KNN with maybe moderate k is a little less complicated than QDA and LDA. If KNN is very large k, possibly much even simpler than LDA. If k is similar to the sample size, and then probably KNN is even simpler than LDA. Yeah, forecasting performance, the simple boundary, probably the LDA or QDA is better, and the more complicated one, the KNN, the simple boundary, the KNN is worst. But complicated boundary, KNN is better, and the QDA is next, and the LDA, logistic regression, are worst. Yeah, so we will see the prediction performance of the classification models for binary classification problems under 6 different scenarios by simulations. And here, the predictor is the 2-dimensional continuous variable x1, x2, and the response is binary. And the examples has been changed from the version 1 of the textbook, edition 1 of the textbook, and edition 2 of the textbook. But these slides are based on edition 1. Edition 2, they have slightly different simulations. And we have 6 different scenarios. The first one, the scenario is the Gaussian density with no correlation between x1 and x2 is given. So yeah, so based on 2 Gaussian densities with no correlation between x1 and x2. So that is, one is like this contour and the other is this contour. So shapes are the same and no correlation between x1 and x2. So contour plots are all the circular. Scenario 2, Gaussian densities with positive correlation between x1 and x2, but it's a common density. So that is basically we have this density and this density. Correlated, but the same for the 2 groups. And scenario 3, the T densities with no correlation between x1 and x2. So basically similar to scenario 1, slightly different shape. So maybe we have this, but much larger as a contour plot, and like this. It's similar to scenario 1. Just distributional assumption is slightly different. So scenario 1, exactly LDA situation. Scenario 3, actually slightly different because it's not Gaussian and it has more heavy tail, and probably the logistic regression works better because logistic regression, basically we assume a more heavier tail. I mean, the larger noise, I would say, or more robust against outliers, we can say. And the scenario 4, Gaussian density with different correlation between x1 and x2 for groups. So the situation is, okay, so one group is like this, and the other group is like this. And scenario 5, the Gaussian densities with no correlation for x1, x1 square, x2 square, and x1, x2. So basically, this predictor space is different. So we have 3 axes. So x1 square, x1 square and x2 square. And okay, so this is 2-dimensional lecture note, but the x1, x2. Okay, then within this space, these two are the same, so that some contour plot this. The no correlation. No correlation. So like this and like this. Okay. But the space is different. The scenario 6, it didn't give the details, but the more complicated, the non-linear rule. So the KNN expected to work better. Okay, so scenario 1. So this is the underlying assumption is LDA. Then LDA is the best. Logistic regression is similar, so it's the second best. And QDA, the additional parameters, it performs worse. And KNN, it's worse because we don't need that complicated assumptions. KNN CV means the choose K by some simulation method, so-called cross-validation. We will cover it later. Scenario 2, this is also this is what the Gaussian positive, still LDA situation. So LDA is the best, almost the same, and logistic second, and others are worse. So scenario 1 and 2 are similar. Scenario 3, the Gaussian assumption is violated, so the logistic regression gets better, and the LDA gets slightly worse, but other are off the correct model, so the performance is worse. Sorry, the y-axis is some classification error rate, I think. Maybe we should use AUC rather than that. But scenario 4, that is QDA situation. So the QDA is correct model, so the performance best. And the LDA logistic performs worse. And the KNN, it's similar. KNN with the optimal K, actually better than LDA and the logistic, but worse than QDA. Of course, the QDA basically means we know the correct model. Scenario 5, this is, okay, so LDA for x1 square and x2 square and x1, x2, but in the sense that we have quadratic terms in the model, that it's a kind of similar to QDA situation. So QDA is not exactly the correct model, but still the QDA performs good, and KNN almost performs as good if the K is chosen optimally. And LDA and logistic, actually the truth is more complicated. So these models perform terribly. And the scenario 6, it's very complicated, and no model can detect the correct specification. So more flexible model, KNN with cross-validation, cross-validated K, that performs best. So you can see the KNN does not perform well unless we choose an optimal K. K is equal to 1 isn't good. Maybe more moderate K, like square root of n, then maybe it performs better. But anyway, so KNN performs good, and the others performs worse. So that's the overall comparison of these methods. Yeah, do you have any questions? What time? This 7.
When you say KNN CV, I'm assuming like what that means is that you may have already alluded to this. Is that the KNN CV is where you use the K that gives you the best performance metric, whatever you define that as, when you try a whole bunch of different values of K, and then you then you do cross validation.
Values of K.
Yeah.
Yes.
Okay. Yeah.
So to be exact, the cross validation. Cross validation is yeah, I will explain in a later chapter, but the cross-validation is the method for evaluating test error size. So if we have data, we divide the data set into the subset, the 1, 2, 3. And we use the first two as training, for example, and the last one as test. And we repeat this 3 times with different settings. So we have, suppose that we have the same separation of 1, 2, 3. Then we also try to use the second data set as test set next time, and the first data set as test set also. Then we calculate the error size, maybe error rate, and calculate error rate, and take average. In this way, we can evaluate the model performance. So this is a kind of the training and the test set approach, the validation approach. So we do this for each K, for each choice of K. We try this. Then we can compare the error rate of the each model. So basically, if we have K is equal to 0 to 100, and we have the error size, maybe average error size, then we have like this, then this is optimal K. And we use this optimal K for the model. Yeah, so this is the KNN with the cross-validated K. Yep. Okay, so maybe we have some break. Do you have any questions or any comments? Artificial intelligence is really a hot topic these days. And today, do you know that the Google's the stock price, the Alphabet's stock price, plummeted by 7%. And the reason is that the Microsoft introduced the ChatGPT for search engine, their search engine Bing. So then the Google stock price plummets, even though they also released their version of AI, chat AI, named the BARD, BARD. So AI is good. Yeah, probably a few years later, probably ChatGPT recommends you to buy some products or buy some service. And if you reject it, probably the ChatGPT gets angry or something like that. Yeah, that is the way to make money with AI. Okay, so here, chapter 4 lab to implement logistic regression, LDA, QDA, and the nearest neighborhood method. K nearest neighborhood. And at first I would like to introduce the data. So this is stock market data, S&P 500 stock market index for daily return of this stock index for 5 years. So each year we have about 250 business days. The 1 year is 52 weeks, and each week have 5 business days, and there are some holidays, so about 250 business days. And this is from 2001 to 2005. And this is the data set. Okay, so the first column doesn't really matter. So this is just the maybe January 2nd of 2001, January 3rd, January 4th, and so on. And the stock market return is here. So this is, I think, in percentage. So 0.959%. So the stock market index goes up by 0.959% on January 2nd, 2001. And I would say this is maybe xt. Then log 1 is xt minus 1. This is the stock market return of the previous day. So market return on December 31st. And the 2 days ago, so December 30th maybe. And this is the 1 day ago. So maybe if this is the Monday, then last Friday. So maybe December 27th or something. Okay. And so on. And xt minus 4 and xt minus 5. So you can see that if we see next observation here, then actually the 0.959 is here, right? So next day, this today's return is the previous day's return. So we can see. So you can see these numbers, okay? So these are the same numbers. And this is actually the pretty popular way to put the time series data to be used for prediction. And we have the volume data of the time t, so I would say v sub t, and direction of xt. So this is the response variable y sub t. So this is positive, this is positive, this is negative, this is positive, this is positive, this is positive. So that's why this is up, up, down, up, up, up. And we want to predict this y by these ones. If we use x sub t, of course, we can total x, identify with the y sub t, but we want to use these xt minus 1 to xt minus 5 and the v sub t to predict yt. And there is a context of this problem. So I heard from the economist, and the predicting xt is extremely hard. People cannot make money in the stock market. But the predicting YT is somewhat easier. So direction is somewhat predictable. So that means, for example, maybe we will get, the positive return with 80% probability, but expected positive return is only 1%. And we only have 20% chance that the stock market goes down, but if goes down, we lose 4% on average. Then still, it's a fair, the market. So in this case, it's possible that we can predict the stock market's direction with 80% probability. So namely, the stock market will go up with 80% probability. So the predicting the direction of the stock market is easier than predicting this xt itself. So that is the one context of this problem. And logistic regression, that we can use the GLM function, generalized linear model function, and we can specify family is equal to binomial. If we miss this option, GLM is the same as LM. So we fit the direction on log 1 to log 5 as well as volume. We can specify this data set. So this data set is in the, I think that in ISLR library, ISLR. And we can get the summary of this. And this is the model. This is the deviance residuals. This is kind of the residual, the defined for the binomial, the regression. We won't discuss this in detail. Basically, this is a kind of the likelihood for one's observation. Maybe I would say the negative likelihood. And coefficients are here. So log 1 to log 5, we have coefficients with standard errors. You can see that, for example, this one. So this one divided by this one is the z-value, or in engineering, this is called the signal to noise ratio. So this is z-value in statistics. So this isn't really large. The z-value of more than 2 basically indicates the p-value of less than 0.05. But you can see that all p-values are not significant, meaning the predicting stock market is difficult. And also volume. We don't have much information on that. Yeah, we can use, we don't really discuss it, but based on these numbers, we can test if this model is useful. And at a glance, it sounds this model is useless. At first, we describe the response variable. So we have the stock market goes down on 602 days and the stock market goes up 648 days. It's natural because the stock market goes up over time, so slightly more days for positive return. So 648 over entire sample size is equal to 0.518 or 519. I calculated before class 8. So the baseline accuracy is 51.8%. If we can achieve more than that, then that may be a useful model. And here the R recognized down as 0, up as 1. Probably down comes earlier in the dictionary order. D comes before U. And this is fitted probability. You can use fitted GLM. And fitted probability for the first observation is 50.7%. So based on the lag values on the January 2nd, 2001, the model expects that the stock market goes up with probability 50.7%. Next day, 48.1%, and so on. We can do that, the same thing by this predict function with type is equal to response. We can also detect the coefficients. Also, we can manually calculate these numbers as this. So coefficients of the linear, the logistic regression and the predictor value. This is coefficient and the predictor value. So this is for first observation, Then you get this. Then we use the logistic function. To transform this number into probability, then you can get the same number. And whether or not probability is larger than 0.5, so you can use this condition vector to get this. So you can say true, false, false, true, true, true. This corresponds to the number obtained here. So positive, more than 0.5, less than 0.5, less than 0.5, more than, more than, more than. So that's why the true, false, false, true, true, true. You can use the contingency table. You can generate a contingency table of this. So direction, so this is the truth. And this is predicted value. And these are correct decisions, and these are incorrect decision. So basically, we have the 145 plus 507 correctly over the total of 1,250. So the correct proportion is so correct proportion is 52.2%. And actually, this is error rate. So we calculate the 141 plus 457 over 1,250. So correct percentage accuracy is equal to 1 minus this number. So 0.5216. So it's slightly better than 50% and also slightly better than the baseline accuracy of 51.8%. But difference is very small. Difference is 0.003 or 0.004. So 0.003 is 1 in 300. So we only have 1,250 observations. So it's only slightly better. And also note that this is the training accuracy. So we use the training data to estimate the model, and we use the training set to evaluate the performance. So usually it overestimates the performance. So we want to use the test data set. So this is test data set. We evaluate that. So at first we calculate the training set. Training data set is the 2001 to 2004. And the test data set is for 2005. So we have 5 years of data. So we use the first 4 years of data to train and the last 1 year of data for test. So here we only use the training set to evaluate. And it sounds the coefficients are totally different. You can see, for example, these coefficients. And we can compare this with the original model. Negative, negative, positive, 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 positive. So maybe signs are the same. Still 80% of data are from the same, but for example, this sign changes. And estimates are also kind of close, but are different. Yeah. Yeah, we don't discuss in detail of this test result, but it sounds that still the model is useless. These p-values are all large, not significant. And we calculate fitted value for test data set. Fitted value for test set. So this is test set. And we decide whether or not this is more than 0.5, so 50%. Then we make a contingency table, only about 250 observations. And actually, this is correct for 77 point plus 44 observations, and out of all observations. And error rate is actually the 52%. So correct rate is 48%. That is useless, right? So more than 50% incorrect, even worse than random rule. Yeah, but you can see, so this basically wants to explain how to calculate fitted value for test set. Okay. So you can specify this. This is actually formally, this is a new data option. New data is equal to. Yeah, but this is data set, so R recognize automatically this is the new data set. Yeah. Yes. So yeah. So this. Yeah. So okay. So this is slightly different. So this is the same. The predicting the fitted value for test set, but this is more artificial test set. So we have some artificial numbers. So that means, for example, the log 1. So this assumes the stock market return is 0 in the past 5 days. Or stock market returns are all small positive numbers in the past 5 days. Or the 1 day before stock market has a large negative return, but before we have 0 return. We have these 3 scenarios, and we want to put this to estimate probabilities. And in all of these scenarios, actually the probabilities are more than 0.5, especially the last one, more than 0.5. In old days, when we have large negative return in the previous day, then after the market closed, the people decide to buy the stocks on the next business day, so the stock market is likely to go up. So these days market is more efficient, so probably this probability is very close to 0.5, but the still in this case the more than 0.5. Yeah, yeah, maybe other things are also some also from some the insights that the stock market is very stable and going up steadily, then the probability to go up is slightly more than 50%. And the first one is just a baseline scenario, so it's close to the baseline probability of 0.518. So actually these two are really close to 0.518. Any questions for logistic regression? And next one is LDA. So, okay, so we don't discuss the algorithm, and we just use this LDA function in the MASS library to fit. The format is similar. Here, we only use lag1 and lag2. I don't know the reason, but we use the training set to evaluate it. And you can get these numbers. These are the means for the case that stock market goes down and goes up. So in the past 2 days, stock market, sorry, the stock market is down. Then in the past 2 days, the return are likely to be positive. I mean, on average, and up actually likely to be negative. So we have some negative correlation between the some days stock market return and the past 2 days of return. And here, the coefficients of linear discriminant. So what linear combination of lag1 and lag2 is useful to predict the stock market direction? And actually, that is 0.64 times lag1 minus 0.51 times lag2 is the best linear combination to predict the stock market direction. So those numbers appear here. This model is what? Plot LDA1. Group down, group up. It's not very clear what this means. Yes, sorry, this isn't very clear for me what this means. Oh, sorry, this is distribution of this linear indicator. So this is the best linear combination of lag1 and lag2 to distinguish this group and this group. And you can see slightly that is to have different distribution. So this indicator is slightly smaller for the days that stock market goes down, and almost zero on if the stock market goes up. But still, it's very hard to distinguish, but this indicator is the best indicator to distinguish these two distributions. And also, we can still use the predict function to calculate the fitted value. And I think the fitted probability isn't here, but yeah, so the LDA function, yeah, so basically it returns the just predicted value as the binary scale. It's possible to calculate probability as well, but this predict function returns the up or down. And actually, for first 6 observations, the LDA predicted that the stock market goes up on the day. And in this case, actually, this model performs much better. I think this is for the test data set. So we use the only training set and to train, and we use test data set to evaluate. And actually the 141 observations are correct out of about 250 observations. And no, the other way around, 100. Yeah, sorry. So this is not really error rate. So this is accuracy. And accuracy is actually 56%. So it's much better than the baseline of 51.8%. So we are hopeful that this model can predict stock market better. And the next one, the QDA. You can just change the LDA to QDA. So the models are different, but the coding is the same. And actually, it achieves even better prediction. 151 observations are correct out of 252. So this is, again, accuracy. Accuracy is about 60%. And lastly, the KNN. KNN is more kind of logical, the input and output. So we have to input these things. So predictors for training set, predictors for test set, response for training set, and the value of K. And you can put in this way. We defined training and the test sets first. Then we can put this. Then we can immediately make a table of predicted KNN value. That is just by KNN function. Then this is the truth. Right? This is truth. So response for test set. Then you can see that these are correct and the off-diagonal parts are incorrect, and actually only 50% correct. So this does not work well. But if we use K is equal to 3 in KNN model, sorry, previously K is equal to 1. So basically we choose the past to predict the next day's stock market return, but it does not work. K is equal to 3. We choose the 3 closest days to that day. Then the prediction performance gets better and 53.6%. So this is KNN and LDA, QDA. I think this may be interesting. So if you make a website to predict the stock market return of the next day, it can be popular. Maybe it's hard to update every day, but it may be good. I think practically, so this is the end price. So the end price of this day T and day T plus 1, and end price of day T plus 1, and we calculate return. But probably if you want to develop a website, probably you have to focus on the start price of stock price someday. So start price of T plus 1 days and end price of T plus 1 days. Because after market close, already some information becomes available. So probably if you compare this return and you predict it, then it can be popular among investors. Okay. Sorry, we only have 8 minutes, so we can discuss this. Yeah, but I think I don't really have enough time. Yeah. What should I do? Do you have any questions? Yeah. Yeah, maybe sorry. I think I don't really have enough time to discuss this, so maybe I can just explain the sum of the code here. So this is so-called famous iris dataset. So iris dataset is this. So 3 species of iris flowers, 150 observations, 50 observations each for the species. We have 4 variables, the sepal length, sepal width, and petal length, and petal width. And we can separate these 3 groups. We can demonstrate this graph by just using pair function, and you can use the color option in the graph. Yeah, you can see color. So color is either 1 or 2 or 3. And color 1 means black. Color 2 means red, and color 3 means green. So just specifying this option, that you can just make this colorful graph. Yeah, so this is kind of meaningful. And the LDA, QDA, that you can separate, classify this one. And we have some visualization tool to distinguish these 3 classes. So you can see that these 3 classes are here, they're distinguished by the letter. So 3 species, Setorsar and the Barsai color and the Virginica. Setorsar, Virginica, Barsai color and Virginica, maybe. And this, pale blue, white, and pink are the estimation result by LDA. So this LDA decides that this area is for Setorsar, this area is for Barsai color, and this area for Virginica. But and this is the one predictor, and this is the other predictor. But obviously the the weak point of this method is we can only use the 2 variables. Yes, in general, we have more predictors, and we cannot make a graph of more than 3 predictors. So generally, we can put more predictors, and we cannot make a graph. Yeah, but still, yeah, so that's it. So that is what we did. And you can see this is the quadratic discriminant analysis boundary. So we have 3 groups, and we have the 3 boundaries. We have boundaries, and the boundaries are hyperbolic. Yeah, so this isn't super useful if more than 2 predictors. And yes, so for each method, you can make this kind of the contingency table, and you can see that we can almost, correctly identify the groups. And here, QDA, yes, yeah. So out of 150 observations, only 3 observations are misclassified. So that is probably, yeah, this one, that one, and maybe this one, E here. And I cannot really see the other. Sorry, I don't know. So the correct one is I, but the misclassified. So maybe, yeah, you can see probably 2 I's here, 2 I's here. So these 3 observations are misclassified. Yeah, so that is what the slides discusses. Okay, so we now ends the chapter 4. So do you have any comments? Yeah, so if not, it's the end of the chapter 4. So see you next week, next Monday.